Let's say we have an election in a small town, and these are the candidates: Alice, Betty, and Charles. Voters are given ballots where they can rank their favorite candidate down to their least favorite candidate. This ballot, for example, ranks Alice first, Charles second, and Betty third. Likewise, this ballot ranks Betty first, Alice second, and Charles third. In our election, all of the ballots come in and we end up with this table. This row means that 129 voters ranked Betty first, Charles second, and Alice third. This row means 86 voters ranked Alice first, Betty second, and Charles third. Just from looking at this table, we can quickly see how it might be tricky to pick a winner. It seems like Alice and Betty were both liked by a lot of voters, but Charles was the least disliked by voters. One way we could do this is by counting up how many times a candidate was a first-choice candidate. When we do this, we can see Alice was the first-choice candidate for 150 voters, as was Betty, and Charles had the least, with just 75. As you can see, Alice and Betty seem equally liked amongst voters. So who do we pick? This is where we can use ranked choice voting algorithms to determine a winner. The first algorithm we'll cover is Borda Count. Let's simplify our election down to using smaller numbers. With Borda Count, we will assign what is known as a Borda score for each candidate. We'll keep track of those in a table. Now let's go into a ballot and assign each candidate points. Typically with Borda Count, we give the candidate in last place 0 points, and all preceding candidates get 1 more point up until the first choice candidate. To calculate the Borda score for a given ballot and candidate, we will multiply the number of votes that ballot received by the points we assign the candidate. In our case, Betty would get a score of 16. We can then add this to the table. We again do this process for Charles, who only gets a score of 8. Finally, we repeat this process for Alice, who gets 0 points, as she placed last on this ballot. We then repeat this entire process for every ballot in the table, adding each candidate's associated score into a running sum. When that's done, we can look at the table and see that Betty has the highest Borda count, making her the winner of this election. Another way you can look at Borda count is by looking at a weighted average of where the candidate placed on the ballot, with the weight being the number of votes that ballot received. If we go through this process, we can see that we end up with the same result as before, where Betty is the clear winner and Alice and Charles are tied in last. There is one slight issue with Borda count, though. Let's take a close look at this other sample election. There are a total of 27 votes. When we look at a pie chart of how frequently a candidate was ranked first on a ballot, we see that Alice is picked a majority, or more than half the time. So it would make sense that Alice is the winner, right? Well, if we run this through Borda count, we see that this is not quite the case. Betty somehow wins this election. This is because Borda count does not satisfy the majority criterion, which is one of many criterions used to determine the effectiveness of a ranked choice voting algorithm. Failing to satisfy the majority criterion essentially means that a majority of voters will be left unhappy, which is not necessarily what we want our voting algorithms to do. An algorithm that does satisfy this criterion, though, is instant runoff voting. To find the winner of an election using IRV, we follow these steps. First, we count the number of first-choice votes a candidate received. If a candidate received a majority of the first-choice votes, then they are the winner. Otherwise, we eliminate the candidate with the lowest number of first-choice votes and redistribute their votes. For simplicity's sake, our redistribution process will be taking them off the ballot. But there are many creative ways of doing this. We repeat these steps until either we find the candidate with the majority of first-choice votes, or until there is only one candidate left. In this election, if a candidate receives 14 or more first-choice votes, they are declared the winner. When we draw the pie chart with the first-choice votes, we see that no one got more than 14. So in this case, we will remove Charles from all of the ballots. Now we rerun these steps, and we see that Betty got more than 14 first-choice votes. So therefore, Betty is declared the winner of this election. IRV has been starting to get implemented a lot in the real world recently. It's also convenient that it is so simple for the average person to understand, which is crucial for ranked choice voting algorithms. The next algorithm we'll look at is Condorcet. Condorcet is a pairwise algorithm, meaning we'll first have to find the pairwise scores for every pair of candidates. After this, we'll find the winner of each pairwise comparison. And if a candidate ranked above every other candidate in that comparison, then they are declared the winner of the election. Let's look at an example. First, let's create a table to keep track of all pairwise scores. Now let's look at each ballot. With this ballot, we can see that Betty wins over both Charles and Alice, and Charles wins over Alice. We then update the pairwise table with the number of votes that ballot received. We continue this process for every ballot in the election. Now let's look at each pair of pairwise comparisons. Let's start with Alice and Betty. When we look at their corresponding entries, we see Betty ranking over. Alice occurred more frequently than Alice ranking over Betty. So we can mark Betty ranking over Alice with the value 1, and a 0 for Alice ranking over Betty. Likewise, when we look at Alice and Charles, Charles ranked over Alice more often than the other way around, so the table gets updated like so. Lastly, we update the table for Betty and Charles's pairwise comparisons, and we end up with this table. Here we can see that Betty won against all other candidates in the pairwise comparisons, which makes her the winner of this election. Another way of thinking about this table is a graph. If we look at vertex A, we see that it loses to both B and C. Looking at vertex C, it loses to B. B is the only vertex without any outgoing edges, which makes B the clear winner. These graphs are used in other, more complex ranking algorithms, which we'll cover in the next video.